ٹاکس میں آپ کا خوش آمدید. جیسا کہ آپ جانتے ہیں ہم اس میں کشمیر کے سائنٹسٹ سے بات کرتے ہیں. تو اس میں جو ڈفرینٹ فیلڈس ہیں, اس میں جو ہمارے سائنٹسٹ کام کر رہے ہیں, ہم ان کے ساتھ بات کرتے ہیں, ان سے پوچھتے ہیں ان کا کنٹریبیوشن کیا رہا سائنس کا جو نالج کا اوشن ہے اس میں آپ کے کتنے ڈراپس ابھی تک آ گئے ہیں, کتنے آنے کی اور امید ہے. تو اس سلسلے میں آج ہم نے دعوت دی ہے ڈاکٹر گلزار احمد بٹ سے. یہ اس وقت سری میں کام کرتے ہیں ایز اسسٹنٹ پروفیسر سائنٹسٹ ہیں. تو یہ بیسیکلی کیمسٹ ہیں. تو کیمسٹری ایک بہت وسیع سائنس ہے, لیکن اور کیمسٹری تو ہے ہی, جسم میں اپنی کیمسٹری ہے, لیکن ہم جس ایکو سسٹم میں رہتے ہیں اس کی ایک کیمسٹری ہے. اور سب سے بڑا جو مسئلہ ہمارے ہاں ہے اس وقت, جو چیلنج ہے وہ اوزون لیئر ہے یا کلائمیٹک چینج ہے. تو اسٹیٹس کیا ہے اس میں ریسرچ اوور آل. میں آپ کی ریسرچ کی بات نہیں کر رہا ہوں, میں کہہ رہا ہوں دنیا میں اس وقت جو ریسرچ ہو رہے ہیں اس کے گول پوسٹس کیا ہیں اس حوالے سے.
So if we look into the climate change, like if you see the world, it's a big threat right now going on. If you see around the globe, a lot of research is going on in the direction that how we can address this problem of climate change. So one thing which you have addressed here is carbon dioxide. If we have higher concentration of carbon dioxide in the atmosphere, the CO2, which is called the greenhouse gas. So increasing this concentration in the atmosphere, it also leads to a global warming. So different people are addressing this problem differently. So during my postdoc, I have started to use this carbon dioxide as a starting material, as a monomer for making polymers. So what we do actually, we capture the carbon dioxide from the point sources. Like if we have an industry, around the industry we have the MOFs, metal organic frameworks, we use them and they can capture the carbon dioxide, and then we use that carbon dioxide which is captured from point sources, and then we use that as a monomer for making these polycarbonate.
ایک بات میں آپ سے عرض کرنا چاہوں گا کہ یہ جو کلائمیٹ چینج والا مسئلہ ہے بہت ہی نازک مسئلہ ہے. جو کشمیر کی بات ہم لے لیں, یہ ویلی ہے, ہر طرف سے پہاڑ ہیں, پہاڑوں سے گری ہے, لیکن سائنٹیفک انپٹ ہے ابھی تک کا کہ ہمارے ہاں جو درجہ حرارت میں اضافہ ہوا ہے وہ باقی جو دنیا کی درجہ حرارت میں اضافہ جو ہوا ہے اس کے مقابلے میں ڈبل ہے. اور اندازہ یہ کیا جاتا ہے کہ آنے والے 100 سال میں جب پوری دنیا میں درجہ حرارت 0.5 ڈگری سینٹی گریڈ بڑھ جائے گا, کشمیر میں آنے والے 100 سال میں 3 ڈگری سینٹی گریڈ کا اضافہ ہونے کا خطرہ ہے اگر ہم کسی طرح سے گرین ہاؤس گیسز کو مینیج نہ کر پائیں. گرین ہاؤسز میں کشمیر کا اتنا کنٹریبیوشن نہیں ہے, چھوٹی جگہ ہے, لیکن دنیا ایک انٹیگریٹڈ ایک گلوب ہے. یہ تو صرف انٹرنیٹ میں ہی کنیکٹڈ نہیں ہے, سسٹمز میں بھی سب کنیکٹڈ ہے. تو ہو سکتا ہے کہ کہیں اور ٹینشنز ہوں کلائمیٹ کے حوالے سے تو ویسٹرن ڈسٹربنسز وہ سب ہمارے آنگن میں چھوڑ دیتی ہے. تو لیکن انسانی معاملے پر بات کرنے سے پہلے ڈاکٹر صاحب میں آپ سے یہ پوچھوں گا کہ آپ کا سری میں ایک سائنٹسٹ بننے سے پہلے آپ کا جو سفر رہا نالج ایکوائر کرنے کا اسکول سے لے کر اب تک, وہ کیسا رہا؟ اس میں کیا کیا سنگ میل رہے؟ What were the milestones?
I am from a rural area in Ganerbal. Kurahama is a place there, is a small village.
I know it.
So I did my schooling from there, and I did my schooling from government school. Mostly it was from government school. After my 5th standard, I was in an English medium school there. It was not English medium that time, and then it transited to an English medium. And then from 5th standard, I was in government school, government high school, Kurahama. And then after that, I moved to higher secondary school, Ganerbal, where I did my 11th and 12th. And then I joined SP College, Srinagar, for my undergrad courses. Yeah. And after completing my undergrad from SP College, Srinagar, I joined University of Kashmir in 2008, while I got admitted for Masters in Chemistry. So I completed my Masters in 2011, and during this time I qualified the National Eligibility Test NET, and I was the people who get on the top ranks in NET, they are being awarded the JRF, Junior Research Fellowship. So I got the JRF, Junior Research Fellowship, and under that fellowship you are opt for any institute in India, any national institute for PhD. So I also applied for a couple of places, and eventually I joined IIT Bombay for my doctorate studies. And during doctorate, I worked with Professor Ramaswamy Murugavel, who is one of the leading scientists in synthetic and inorganic chemistry there. And after completing PhD in 2018, I moved to United States and joined Professor Donald Danisberg at Texas A&M University for my postdoctoral studies. And then I moved back in 2021 under the Ramanujan Fellowship Scheme. It's a brand gain fellowship, which is given like for the top most scientists who are abroad, and to motivate them to come back. This fellowship has started earlier. And so in this fellowship, like you have to submit a proposal, and people who are of Indian origin and they want to come back, so they have to apply, and then it's very competitive. Like around the year they take around 30 people in all streams of STEM, science, technology, engineering and mathematics. So in chemistry they take 4 or 5 people every year.
So let us go back to your PhD. So PhD में आपने किया क्या? मतलब अगर हम आम लोगों से बात करना चाहेंगे कि मैंने PhD में क्या किया, तो what were the takeaways from your PhD?
Yeah, my PhD thesis was on synthetic and material chemistry aspects of metal monoalkali and monovalent phosphates. अगर आप broader perspective में देखना चाहेंगे ये क्या है actually, उसमें हमने क्या किया? We have used some ligands. These are the entities which we coordinate to the metal and make the metal complexes. So उसमें मैंने metal phosphates को use किया as ligands to make 2D materials. 2D materials actually अगर आप देखोगे 2010 में Nobel Prize मिला है 2D materials पे ही. उन्होंने क्या किया actually graphite से exploit करके उन्होंने first single true 2-dimensional nanosheet बना दिया है. तो हमने यही 2D material बना दिया है inorganic वो organic है जैसे carbon से based है. यहाँ पे हमने inorganic 2D materials बनाए हैं by using these phosphates as ligands and making the 2D complex of that. And then we have period of these multi-layer 2D complexes layer by layer and exploited it to make a single nanosheet of 2D material. और उसके बाद हमने उसको energy related applications देखे हैं like capstans energy storage के लिए हमने उसको use किया है उस 2D material. So this was during my postdoc was mostly around that. Also another aspect which I would like to say here is that the materials which I synthesized during this PhD, they are like thermolabile. So we can make ceramic materials, ceramic phosphates from that. So if we heat these materials above 250, the organic part gets evaluated in the form of gas like ethene, butane, and then it leads to the formation of pure ceramic materials. So, but when I moved to the postdoc, I switched my field. So I have started to work in like polymer chemistry, and my postdoc was mainly on like how we can work on sustainable chemistry. It was on sustainable chemistry. How we can use carbon dioxide as one of the monomer and then make polymers out of that, which are having diverse applications. Then
तो मैं थोड़ा नाज़रीन को ये समझा दूँ, ये जो हम ऑक्सीजन लेते हैं और कार्बन डाइऑक्साइड छोड़ते हैं, हमारे जो पौधे हैं वहाँ उनमें वो कार्बन डाइऑक्साइड का इस्तेमाल करते हैं अपनी एनर्जी के लिए और ऑक्सीजन बनाते हैं. लेकिन इस सब के बावजूद एक बैलेंस में एक तफावत हो गई जिसकी वजह से कार्बन डाइऑक्साइड में इजाफा हो रहा है हमारी फिज़ा में, और उसकी वजह से ग्रीन हाउस इम्पैक्ट, मतलब ये ग्रीन हाउस गैसेस जो होती हैं उससे हमारी फिज़ा को प्रॉब्लम हो जाती है. और ये हमेशा चले ही रहा है हमारी साइंस का, हमारी केमिस्ट्री का, जो बाकी फील्ड्स हैं साइंस के, कि किस तरह हम, क्या कोई ऐसा पॉसिबिलिटी है कि हम ऑक्सीजन, हम फिज़ा से कार्बन डाइऑक्साइड की जो मिकदार है उसको किसी तरह से कम करें और किसी तरह से ग्रीन हाउस गैसेस का जो इम्पैक्ट हमारी फ़िज़ा पे है, हमारे मौसम बदलते हैं, हमारी ग़िज़ा जो फूड चेन इम्पैक्ट होती है, तो ये पूरा जो प्रोसेस जो गुलजार साहब बता रहे हैं ये उस प्रोसेस का हिस्सा है. तो क्या क्या आपने फिर को इसमें पोस्टडॉक में?
तो पोस्टडॉक में हमने यही मतलब मेन इट वाज ऑन कार्बन डाइऑक्साइड कैप्चर एंड यूटिलाइजेशन. नॉट ओनली कैप्चर, अगर आपने कार्बन डाइऑक्साइड को कैप्चर किया है देन इट इज लाइक व्हाट यू विल डू विद दैट कार्बन डाइऑक्साइड. सो वी हैव नॉट ओनली कैप्चर्ड द कार्बन डाइऑक्साइड, we have captured it from the point sources and then used it for making useful polymers. Nowadays you might be hearing a lot about like circular economy. It is, as I was saying in the beginning of this talk, like it is a sustainable chemistry where we go make around like we use the same carbon dioxide which is coming as a waste somewhere and then making the material out of that which has many applications. So in principle how we do that I would like to show here. Like we take a reactor, metallic reactor. This is a custom designed reactor. We have designed it like my professor at Texas University. He has first time made this reactors. It's a machine in a machine shop. So we have custom designed these reactors. And then what we do actually, we In this chemistry, we take one carbon dioxide as one of the monomer, and then we take epoxides. And in presence of catalysts, some homogeneous catalysts, metal silane complexes, we use that as catalyst for catalyzing this reaction. As you know that like CO2 is highly inert. For making this to happen, we use high energy molecules like epoxides. They have the ring strain, and we use that ring strain energy for making this process to happen. So what we do actually, we take the epoxide catalyst in this reactor, and then inside the glow box, because some of the epoxides, they are sensitive to moisture and oxygen. So we have to do this process in a glow box in Chile. So we take it inside the box and then add these like CO2 and this epoxides and the catalyst, and then we close the reactor. You can see here, we close it. We close it tightly, and then we take the reactor out of the box, and then we simply take it to a place where we have stored the CO2. It can be another reactor. We are connecting in a parallel another reactor, and in that reactor we have a MOF, and in the MOF the CO2 is absorbed. We heat the MOF, it releases the CO2. Because these metal organic frameworks, they have pores with specificity, like some MOFs they can absorb CO2, some can absorb methane, like that. So the MOF which we are using, it has high tendency to absorb CO2. Then we heat that MOF, and due to heating, the carbon dioxide comes through another tubing and gets inserted inside this reactor. And then we allow this reaction to happen for 24 hours. And then next day when we come, we can see a beautiful like polymer is formed inside that. And then we do some purification, and we are getting like polycarbonate polymers. If we take epoxide, propylene oxide, we get polycarbonate polymers. This is a 10 milliliter reactor, and we have done in our lab also, we have used a 25 milliliter reactor, you can see here. So, but we can make it in kilograms, in tons, this polycarbonate can be made. Currently, companies like Covestro and others, Ormico, they are using the same concept and making the foams. They are making the polyols. Polyols are like the building blocks for making polyurethane. You know the polyurethane industry is one of the leading industry right now in manufacturing different products. So for making those polyurethane, you need a starting material called polyols. So these polyols can be easily synthesized from this CO2. So in that way, like it still adds to towards the circular economy. Because naturally earlier they were making those polyols from petrochemicals, like the petroleum-based products.
So, but the larger thing which I wish to ask you is the polymers that we will be making using this process, are these the same plastics or these are biodegradable ones?
No, these are biodegradable. If you see these, as I told, these are called polycarbonates. They have the carbonate linkage. So the carbonate linkage is susceptible, like there are already research done in this, why these polycarbonate polymers have shown they are biodegradable. They cannot remain in the ecosystem throughout, like how their lifespan is like 8 to 10 years. And the important thing is we can collect these polycarbonates, and then we can use the microorganisms, like as I say, they are biodegradable. And they can be converted back to their monomers, and these monomers can be used again for doing this polymerization. So the important aspect which I would like to say here is, please, I have first time introduced like functionalization in these polycarbonate polymers by using well-defined metal complexes. So we have a well-defined metal complex where we can have varied types of metals, like metals which are good for catalysis, metals which are good for drug delivery. So we can use that and insert by using a concept called as chain transfer chemistry. So we have used that chain transfer chemistry and then inserted these well-defined metal complex in the backbone of these polymers, and then we can use that for drug delivery. We can use that for like micellar catalysis, because we can not only make polymers of one monomer, in that we can have different types of monomers, like block polymers. And if we have a block in which we can do functionalization later on, like if we use AGE, allyl glycerol ether, it has a double bond. So the double bond can be later on functionalized, and we can make micelles out of that. So these micelles have like hydrophobic and hydrophilic segments. So if we want to use a drug, if we want to transport it inside the body, it should be soluble in water. So for that, we have like these micelles are formed in water. We can form in these micelles in water, and these micelles have the metal complex of choice which we can use. and that metal complex can be a drug, and then we can use that bicycle phase for transportation of this drug.
Has this idea been ever talked to the industry?
Yeah, like as I said earlier, like currently Covestro, Armeco, Covestro is a company which is currently using the same concept. They are using the sustainable chemistry, using carbon dioxide and epoxides and making the foams or polyols for polyurethane industry by using this concept.
तो जो आपने इतना काम किया इसमें, मतलब इसमें ऑलरेडी किसी ने कोई काम किया था या what makes your work completely different from all others जिन्होंने अभी तक काम किया?
Yeah, the point is like there are a couple of scientists who have established this research area. Professor Donald Danisberg, who was my postdoc supervisor, he is one of the pioneers in this area. Besides that, there is Coates. He is also in US Cornell University. Or there is Professor Williams. She's in Oxford University. She has also developed an industry. Like she has also industrialized this concept. So the thing is, my part in this was like how to introduce the metal complex in that, and also we have made different. Recently, I used one eugenol. Eugenol, as you might know, is a natural product, and it is very cheap in India. Like it's in kilograms, its cost is very cheap. So we have made polymers from that eugenol. We have used it, as I said, this polymers needs two things. One is CO2 and epoxides and the catalyst. So we use it eugenol, it's a natural product, and converted it into polymer.
ये पहली बार हुआ?
Yeah, this is the first time which I have done this. Like we have made the polycarbonate polymers from this eugenol.
So there is a possibility that we can use polymers to push away the problematic plastics by using cheap materials in making them.
Yes, it has a societal. The cheap material is actually, this process is green in nature. It's comes under the green chemistry concept, because you are using the waste product carbon dioxide, and also at the same time you do not need to use any solvent. If you know, like if you can, in a broader perspective, which I will say, like if you want to do any chemistry, any reaction, you need to have the reactants, and you need to dissolve these reactants in some particular solvent, and then convert it into products. Like this is what is happening on majority of the cases. So in this case, we generally don't use the solvent. We use the excess carbon dioxide, which acts as a solvent also.
How far away are we having plastic chairs or plastic crockery using this method? When it is possible?
No, it has been implemented. Like this method has been implemented for making lots of goods. As I said, like foams have been made by that. And the thing is, like which I was saying, we have recently used these block polymers where we have two different blocks which are connected chemically, and then one block has the possibility of doing the functionalization, and we have used those block polymers as inks for 3D printing. As you know that 3D printing is used for doing a lot of things nowadays. So we have used those polymers as inks for doing 3D printing. The advantage of using these inks is that they are biodegradable. If you have a 3D structure, if you want to use it for some particular purpose, and after that you want to discard it, you can simply recycle it. You can easily recycle it. For example, these polymers, if you add them in basic conditions, they get back converted to monomers. That's one thing. Another thing is, like in the 3D printing, if you want to print a substance, which need to have a particular type of hardness or softness. Like if you want to print a substance, we should compress and come back to the form. So we can tune the hardness and softness of those polymers or those inks. We can formulate the inks accordingly. Because, for example, I will cite here one example. If we use cyclohexene oxide, it's an epoxide, and if we make a polymer from cyclohexene oxide, it is hard in nature. And then if we have a polymer from butylene oxide, polybutylene oxide, if we make that polymer, that's very soft. So in that case, if we make a block polymer, having both, one segment of polycyclohexene carbonate, another segment of polybutylene carbonate, and if we link them covalently, which we have done, and in that we can change the ratios of one block and another block so that we can achieve a particular type of hardness and softness. So we have done we have shown one paper which is under review right now in Angewandte Chemie. It's one of the big papers in Wiley Communications. So in that we have shown that how we can formulate this ink by using this concept, and how those 3D printed structures are different than the normal classical used inks.
So what is the core focus in your research at Siri?
So in Siri, I want to continue this research here at Siri. So I want to take this research into, expand this research in different directions. As I mentioned to you earlier, like eugenol. So eugenol has the possibility of functionalization. So I want to make the metallopolymers by using this eugenol epoxides. And I want to currently focus on two things. One is the CO2, which has the beauty of doing this work. We are capturing the carbon dioxide and using this like utilization of carbon dioxide. And at the same time, we want to use these materials for diverse applications. So like I want to use this for doing the catalysis. Like in micellar catalysis, if we have each micelle which is loaded with the catalyst, if we add it in the water, we can do the chemistry in water. Because most of the catalysis, we need to do the catalysis in organic solvents. So here we can do the catalysis in water by using this micellar catalyst concept. And the important aspect of that is that in each micelle we have a well-defined metal complex. So the local concentration, catalyst concentration can be increased. So the turnover numbers, catalyst efficiency can be enhanced. That's one aspect. Another aspect is that I want to, as you many colleagues here, they work in biological systems. So I want to use these polymers for doing different biological functions. So we want to use these metallopolymers for doing in drug delivery. Like if we take some palladium complex, for example, or some which are biocompatible metals, we use them and we can use those for doing the for studying the biological systems.
So that's
another aspect of it.
Another aspect.
So
how many PhDs are you writing now?
Right now I have given I have joined 7-8 months before. So I have given recently the advertisement for PhD camp from this center. So we are going to take 10 PhD students in total. So I have given 3 vacancies in that. So the thing is, the beauty of doing PhD under Siri is that we have an interdisciplinary background here. So a person who, if he wants to join in chemistry, he will have an opportunity to work in the bio, to work physics, or to work in environmental science, or some other aspects like artificial intelligence, which is right now one of the hot areas. So that's the beauty of doing PhD in this center. So I will be taking 3 PhD students in coming session.
When I was myself a student of sciences, the ideal way of killing time during inorganic and organic chemistry was that I would usually sleep. But this is the first time, the first lecture on chemistry in which I couldn't sleep. So I give credit to you, Dr. Gulzar, and I hope in coming days we will meet again. Thank you, Dr. Gulzar, for
so
all this and talking so much of inorganic and organic.
Yes.
Thank you so much.
Thank you so much.